So we will continue going through these different hydraulic components. Last time we had a lecture, I was talking about hydraulic valves, and today I'm going to talk about hydraulic actuators and how to dimension and select the correct actuators. And we will have time for questions regarding your designing project as well. So let's continue, or let's start. I will share the screen. So hydraulic actuators, this file can be found from Moodle. In hydraulic components, there is this PDF called hydraulic actuators available, and this is the content. So when we talk about hydraulic actuators, I mean hydraulic cylinder or hydraulic motor, but mainly we will concentrate on the cylinders this time. So as it was told originally in the very first lecture, these devices are meant to convert the hydraulic energy back to mechanical energy. And I think this is quite obvious, but when we want to have this linear movement, then we talk about hydraulic cylinder, and when you want to have some rotating movement, then you need a hydraulic motor. But the actuator cylinder is the one which is the most common type. Of course, motors are also commonly used, but still the linear movement is the thing in hydraulics, why it is in many cases better than other options. And as you know, there are two main types of hydraulic cylinders. There are single acting cylinders and double acting cylinders. Single acting cylinder means that you can move the piston only in one direction with the help of hydraulics, and then the returning movement, retracting movement, typically it is made by external force. For example, we will lift the load, and then when we open the road from this plus chamfer back to the tank, then there is some external force which is pushing the piston back in. But in double acting cylinder, both directions, both extending and retracting, can be controlled with the hydraulics oil. And there is a two separate cylinder here. This represents the double acting cylinder, and this one single acting cylinder. But also this kind of a cylinder can be a single acting cylinder, so it doesn't mean that you always would have to have this same diameter thick piston rod, but it works. Single acting cylinder works in this way as well, but then it needs to have some breather valve here, because when the piston moves back and forth, the air there is air inside, and the air needs to come out or needs to get in, so that there is not too much pressure, air pressure or vacuum, and it needs to breathe through this connection. And normally the breather valve is such that there is some kind of a filter, so that not so much dirt can go into the cylinder when the cylinder is breathing. The single acting cylinder, it is quite widely used, for example, example, in different kind of trailers, like in this picture. And in many cases, the trailers, they need to have a very long stroke, and then the standard hydraulic cylinder is not suitable, but you need to have this telescopic cylinder. So in this telescopic cylinder, you have many pistons put in a small package, and when the first cylinder is fully extended, then the next one, which is inside, starts extending, and so on. So they all the time become thinner and thinner and thinner, and also you get less force, but the highest force normally it is needed in the very beginning, and that's the place where you have also the biggest diameter in the cylinder, so it makes sense. These telescopic cylinders also exists as a double acting cylinder, so it's not only a single acting, but it could be also a double acting version. But in the trailers, normally you don't need this double acting function, but the single acting is enough. Then what comes to the dimensioning and selecting the cylinders, it is a very important thing, is to design and understand how the cylinder is mounted. And there you can see 4 basic mounting principles. Foot mounting, so that the cylinder is attached from this and this point, so that there is a rigid attachment to the frame of the machine. Or it can be a flange mounting. This is also a rigid mounting, no movement at all, but the flange can be here. This is so-called front flange, but it could be also in here, and in this case it would be a rear flange, or in some cases the flange could be also somewhere in the middle. Then these two were rigid mounting, so that the frame of the cylinder can't move at all. The cylinder is fixed totally. But then if you want that the cylinder, if you want to allow some kind of movement of the cylinder, some rotating movement, then you need to have some kind of joint. For example, in this case, it is so-called swivel design, so that there is this moving element, the rotating joint over here. Or you can have this swivel mounting with trunnion, so that the connection point is not here at the end of the cylinder, but somewhere in the middle. But I would say that this swivel design, this kind of design, what you can see here, is the most common mounting type of the hydraulic cylinder, because in many cases the cylinder needs to move a bit. It can't be fully fixed. For example, in your case, in this pillar lifter, you need to have, in a scissor lifter, you need to have this kind of attachment, because the cylinder is changing a position while it is extending. And why this is so important? It's because of buckling. And know that the rotation is allowed. So there is a bearing inside. And then in other end of the cylinder, you don't see any connection at all yet, but there will be some kind of either fixed mounting or some kind of swivel also in here.
Okay,
so there is 2 options how to connect the load here with some kind of a joint, or so that it is fully fixed. Okay, but buckling is the thing, and with this buckling formula, you are able to study whether the piston rod is strong enough or not. So this what we are interested in is this D basically here, and this small d now means what is the rod diameter. It's not a piston diameter, but a rod diameter. So normally when you make some calculations that what kind of hydraulic cylinder is okay, of course you use this pressure and you are able to find out the piston diameter, but this is the formula what you can use to find out what is the needed piston rod diameter. And since you have been studying this with Seppo, I suppose that you recognize these 4 different Euler methods for buckling, or is it so?
Yep, it is.
Yes, and here you can see now the difference, that if you have a fixed mounting or some kind of a flexible mounting with the bearing. So the method 1 is so that the cylinder itself is fully fixed, but the load is not supported at all. It is fixed to the cylinder rod, but it doesn't have this horizontal support, which means that we have a method 1, which means that the reduced length, what you have to use in the formula, is 2 times the actual length. Then the method 2 is the so-called basic case, so that 2 ends with flexible guide. And this is the most common case in hydraulics, and this is also the case what you have in your design exercise. But please note that the length what you have to use in this calculation is the distance between the connection point of the hydraulic cylinder. So it is not the stroke, it is not the length of the cylinder, but it is the length between the attachment points. And in this case, the reduced length is equal to actual length. And then if we go to the 3rd method or 4th method, then the reduced length is actually a little bit less than the actual method, because there is more support. In method 3, the cylinder is fixed, the load has a support, but there is a flexible guide. And in method 4, everything is fixed. So the cylinder is fixed, the load is fixed, and it has this horizontal guide, to say so. But this is the normal, typical. Well, all of them are normal, but this is the most common case.
So means we can use the method 2, or?
Yes, you can use the method 2, or you should use, because it's the only one that works in your case. Because if you think about the scissor lift, when you move from a down position to the highest position, the cylinder is not staying in the same angle, but it is changing the angle, which means that you need to have these flexible joints there. Actually, at this point, I could show some example of Bosch Rectroot catalog. I hope this works, because last week we had some problems with this one. So let's go to see cylinders. So at first there is a two main type of hydraulic cylinders available in the Bosch Rexroth. A mill type cylinder or tie rod cylinder. This mill type cylinder is, I would say, more common, and now there is a tool called configuration by technical date. And it begins so that you need to specify that do you want to use a metric system or American system? Well, I want to use metric system. Then I need to define that what is the pressure in system. Let's put, for example, 200 bars and continue. Then what kind of configuration in the cylinder you want to have. A normal single rod, this kind of a double rod cylinder, or a differential cylinder with position measuring system. Well, I want to have this normal single rod cylinder. And now you are able to specify how the cylinder is attached. You will see here the foot mounting. There is a flange mounting. There is another flange mounting. And there is this swivel design. It is called self-aligning levies. So these are the options that Bosch Rexroth has. And for instance, now we could select this self-aligning levies at cap. And then there is some basic settings. I will just put now some numbers here. So let's assume that we have, for example, 3 kilonewtons pushing force and 0 kilonewtons, or not 3, but 30 kilonewtons, and pulling force is 0. Then some stroke length that we want to have, for example, 600 millimeters, and then an installing angle. You see here what it means. Well, I just put, for example, 45. Then other design criteria, this load guided, which I'm not able to uncheck, means that do we have these walls. If I compare here, it means that do we have this kind of situation where is no horizontal support, or is it the case where we have this horizontal support? But since I already selected to the cylinder that there is this joint, and it is not possible to build the system without this support, so I'm not able to uncheck this load guided at all. But this is something that I'm able to select, that do we have this joint here or not. So this is a fixed mounting, and this is the mounting where we have this bearing also here. So this is the case more or less what you have. Then I would be able to specify something related to damping or something else, but I'm not so interested about them at the moment. I just want to go further, so I will press continue. And what we have here, we have some options, and the D, capital D, stands for the piston, and this small d stands for the rod. So it tells me that I need a cylinder with 63 millimeter piston and 40 millimeter rod. And this SF1 this is a safety factor 1, safety factor 2, safety factor 3, and so on. But this SF1 is the most important. It is the safety factor based on buckling. I think it is told somewhere here. SF1 is a buckling calculation safety factor at load pressure. So it is the safety factor what you saw in this buckling formula. And now please remember that now in this first trial we got this 63 and 40. But what if we go back and change the mounting type so that we don't have this kind of self-aligning clevis at gap, but instead we would have a flange mounting. But otherwise, we would have a same situation. And now I would be able to also select whether the load is really guided or not, but I will get smaller. If I want to have a smallest possible piston rod, then I would need to have the load guided without this self-aligning clevis, so that I would have more or less the method 4 case now. Of course, it is not possible, for example, in your case, but I just want to point out that what is the difference. See, earlier it was 40 millimeter that we needed here as a piston rod diameter, but now 28 is enough. And also the piston is smaller, which means that originally in this earlier example, it was not the piston diameter that was the major thing, but it was the rod diameter that kind of drive also the piston diameter, because of course the rod can't be bigger than piston, but normally there is some relation, so that it is not an option to have an 50 millimeter piston and 40 millimeter rod. And now, even though we have this 28 millimeter rod, which is much smaller, still the safety factor for buckling is 4.6, so way higher than earlier. So this is that I just wanted to point out that how important a role this mounting method, and also that you understand how it should be mounted. It plays. It is very important when you design a hydraulic cylinder and select and dimension the hydraulic cylinder.
Excuse me?
Yes.
Can you speak again? Like, why can we just choose one and mounting method?
In your case.
Yes. Normally we have to choose what is the mounting method for uppercase and lowercase, but like in the website you show it's just one end of the cylinder, isn't it?
So if I understand the question correctly, you asked that why you have to select this method 2 in your case, not, for example, method 3 or method 4.
No, I mean like when we choosing the hydraulic cylinder, there's
Yes.
2 end mounting point.
Yes.
And in the website we can just choose one end mounting, isn't it? Or if I miss something.
Okay. Let's go here. So it is true that in this point, you are only selecting the one side, one end,
Yes.
and okay, I will select something else. But this is the place where you select the other end, and they are these two boxes. If you don't have anything here, then it means more or less this case, so that you don't have this support, but the load is fully fixed.
Yes.
And if you select this load guided, the drawing doesn't change at all, but now the load guided means these gray walls here. If you see the difference between the method 1 and all the rest, in here you don't have anything to support the load, but in here there is some kind of support.
Yes.
And then if you selected this box that with fitted self-aligning clevis, you notice that there is a change here in the picture. If I uncheck the box,
Yes.
this joint disappears, and if I check the box, then the joint comes again. And now if the selection is done here, it means that you have this joint, so or method 2 or method 3. And if you don't have this selected, then you have a fully fixed mounting, so that there is a thread and load will be fitted firmly to this thread. And with this option, you have a joint, a bearing.
So without that check, in the end of the cylinder, there's a thread pattern. So we just fix it in the hole, isn't it?
Yeah.
Yes. Yeah, I understand. Thank you.
All right.
So we have to select both to use the method 2, right?
I think in your case, it needs that you will just tell that you need to select this method 2 because you have this moving cylinder, but you don't need to make any mechanical design here. So you just need to calculate the buckling and give arguments that why you select certain cylinder, but that's it.
Yeah, but I mean that when we are choosing the cylinder, we have to select load guided and the other one with fit self-aligning clevis.
The only option is that what really works is that you need to have both of these checked. If you do it another way, then it is wrong.
Okay. Thank you.
And now I had a little bit different selections than earlier. So once again, I got a different rod and different safety factor.
Excuse me. So when our safety factor is important, like
yeah, the safety factor, this Rex route, I think there is some limit that it doesn't even show you some options where the safety factor is too low. But I would say that a good safety factor in this case is something like 2 to 3, something between 2 and 3.
yes, but I mean it's like we have a lot of kinds of safety factor, and in this case the first one is most important. And
yes, that the first one is the most important. That is a buckling in a such pressure what the load makes, the load what you specified, what what kind of buckling safety factor comes in that situation.
Is
And-
there
and-
any case that other safety factor is also play important role?
I would say normally not, because as you can see, most of the safety factor are much way higher. We can see what they mean. So the difference between 1 and 3 is that the 1 is in a load pressure, but if the system pressure is much higher and you would overload the system so that it would, for example, be able to lift, for example, much more that is needed, and you would put there more load, then the safety factor 3 would be maybe something that you would need to study. But in this case, remember that I put there 200 bars, but it is the case that less than 200 bars is enough to lift the load with this 50 millimeter cylinder. And later, if you would select this cylinder, you would need to reduce the pressure, because it makes no sense to use this 200 bars if you can live with much more smaller pressure. So the operating pressure, the system pressure, need to be changed afterwards. You can originally set it to be, for example, 200, and then when you make the final calculation and find out that what is your cylinder and how much pressure it actually needs to lift the load, then the system pressure need to be tuned and reduced a bit.
The safety factor 3 is like we load at maximum pressure, isn't it?
Yes, exactly.
Oh, yeah. Thank you.
And then we would be able to, for example, if we now select some cylinder, then we are able to specify it very deeply. We are able to tell what kind of mounting, well, not mounting, but what kind of pipe connections there are. And where is the hydraulic port located? And then we are able to specify the end position cushioning. Okay, and I think that now it's time to go back here and first talk about this end position cushioning. So normally it is so that if the piston moves faster than 0.1 meters per second, you kind of need some kind of end position cushioning to avoid these very heavy impacts. And the end positioning cushioning works in a way that before the piston hits the end of the cylinder, kind of a main road for oil is blocked, it is closed, and the oil is forced to go through some narrow gap, through some orifice away from a cylinder. So in this case, in this picture, there is kind of a small piece of piston rod coming to the other side of the piston as well. And normally the oil can go from red area to blue area, where my mouse is moving at the moment, through this port. But when the piston comes close enough to the end, this extension of the piston rod blocks this main road, and the oil is forced to go through this way. and there is an orifice, some throttle valve, and it fully very heavily slows down the motion and cushion the heat. And when we want to start moving to other position or other direction again, there is a check valve so that the oil is able to go through this check valve to this chamfer, and it means that the starting is not cushioned, but it is only the end position, or when we are reaching the end. So it only works in one position or one direction. But this kind of end position cushioning can be put to the both sides of the cylinder. So not only so that it works for retracting, but there can be a cushioning for extending motion and retracting motion, both of them. and normally suggested maximum velocity for hydraulic cylinder is around 0.2 meters per second. Of course, there are some special cases where you can go higher, but this is just a thumb rule that this is a maximum limit for normal hydraulic cylinder. So like here, we would be able to select a hydraulic cylinder without any kind of cushioning, or so that there is an cushioning in both sides. And what is the difference between these two? The cushioning length is the same. Okay, this is self-adjusting and this is adjustable, so that in this case you are not able to adjust the cushioning, but it is what it is. But in this case you are able to change it manually. Then the next option here is sealing. So in hydraulic cylinder, normally there are no leakages at all, which means that the volumetric efficiency is 100%. But because of friction, the hydromechanic efficiency is not 100%, but it is something between 85 and 95%. And what has an effect to this friction is the sealing. And in a hydraulic cylinder, there are sealings in the two places. There is a sealing in piston, so that the plus chamfer and minus chamfer are insulated from each other. And also there is an sealing here between the cylinder frame and the piston rod, so that the oil won't leak out of the cylinder. And there are different materials for this sealing and different demands for the sealing. And one thing is that you need to know what is the hydraulic oil or hydraulic fluid what you use, because some sealing materials are not suitable for certain hydraulic fluids. And the other thing is that what kind of hydraulic system you have. Do you want to have a very low friction, so that you have a very sensitive hydraulic system, and you might have even some servo valves or proportional valves, and you need to move the cylinder very smoothly? Or do you have just a rough system where you drive the cylinder from one point to another point, and no matter if there is a little bit more friction or not. But in here, you are able to select between a standard sealing system, which works with the mineral oil, or, well, another standard seal system. It works with the mineral oil, but also with water and glycol. Or you can have some kind of a reduced friction system. It is called servo quality here. So it is for such cases where you want to have this very smooth operation. Or standard sealing system with rotating bands. So okay, in this case, the cylinder would rotate at the same time. It's still more, okay, there is a very many different options. Reduced friction for heavy industry, reduced friction for different kind of oils or fluids. Yes, but if you don't have any servo or proportional system, if you have a normal mineral oil, you don't have anything special, you don't have a need for reduced friction or anything like that, then your selection would be this one, because this is the most cheapest option.
Excuse me.
Yes.
So it is true that normally the hydraulic cylinder is moving straight forward, but like no rotation.
Yes. In most cases, it is like that.
But like if we want it moves straight, but there's some kind of unwanted load that try to rotate the cylinder. Is that still like keeping it not to rotate, or how does it act?
So the sealings are not keeping it without rotating, but it allows to rotate it slightly. But if we go back here and see the cases here, this is the only case where the rotation really is possible. Normally you have such a guiding that, and the other structure, how the cylinder is connected to the machine or device, it is very typical that they will prevent the rotating movement.
So the hydraulic cylinder is not supposed to be like prevent the rotating load, isn't it?
How to say this? Normally it won't rotate, but it is the small rotating. What might happen? It's not harmful, but it is not designed to work so that there would be a continuous rotating movement. Then it's a special case.
Yes, thank you.
Okay, then this configurator, the next question is that do we want to have, or is there a proximity switch or not? So a sensor for end positions. And I think that in many cases you don't need them, but it could be possible to include. Then there are some external or additional guiding rings, not needed. Then you might have some measuring points for pressure. This is a standard pressure measuring port. Normally, you don't need such. Then do you want to have some lubrication for these bearings? Standard version, conical grease nipple. Okay, then a color is, do you want to have the cylinder filled with oil when it arrives? And do you want to have some kind of testing certificate with when you order it? So there it is. And now you would be able to order it or get a SolidWorks model or study more about the documentation. In a similar way that I showed you in this machine design course, how you are selecting this gear motor, it is the same principle in this configurator. And there is a picture about the chosen cylinder. All right. So as a conclusion, when you have to select dimensions for your cylinder, of course, everything begins so that you need to find out that what kind of force you need to lift with the cylinder or move with the cylinder. And then you need to specify that what is the pressure level. And together with these two pieces of information, you are able to calculate that what is the minimum piston diameter which is accepted.
Excuse me, Simo. Yeah, we are freely able to choose the pressure level.
Yes, you are able. But of course, there are some limits. I think the smart pressure level is around 200 bars. It is
200.
okay. Yes, it is okay to have 160. It is also okay to have 240. But if you go more than 250, then you need to have special components, because normally most of the hydraulic valves, they are rated to work in a maximum pressure of 250 bars. So if you select a pressure level which is higher than that, then you have to make sure that all the components that you select to your hydraulic system, they really can tolerate this higher pressure. Okay, but based on this information, you can find out what is the minimum piston diameter. Then you need to study this buckling, and this gives you the piston rod diameter. And like I mentioned, it might be the case that this is a driving feature, so that this piston rod need to be so big that it also makes the piston itself bigger. And if this is the case, then it might be smart to reduce your pressure level. Then what is the velocity of the cylinder? Do you need the end position cushioning or not? And finally, you have to pick a standard diameter for piston and a rod. So you are not able to order a hydraulic cylinder that has, for example, 26.7 millimeters piston and 17.7 millimeter rod, but the diameters are standardized. And you can see the standardized piston diameters here and the standardized rod diameters in here. But the stroke length is normally something that you can specify. So you don't need to stick to some ready or given strokes, but you can more or less specify that how big stroke you need. Of course, there are some limits that you can't go over, but still it's quite free. And you need to remember also that even though these diameters are standardized, the other connection points or other dimensions are not standardized, which means that if you have, for example, this Bosch Rexroth cylinder in your system now, and then you need to replace it, you can't select another manufacturer without checking that it really fits there, because it's not a standard that defines all the dimensions. In pneumatics, it is different. In pneumatics, there is standards, and if you buy, for example, a Festo pneumatic cylinder, and you need to replace it, you can very easily buy an SMC pneumatic cylinder, and it goes there without any problem. But it's not the case in hydraulics. Then a couple of slides about hydraulic motors. Hydraulic motors are very similar than hydraulic pumps, and there are different operating principles, different types of motors and pumps. There are vane pumps and axial piston motors and pumps, and radial piston motors and pumps, and gear pumps, gear motors. So they have the same mechanical structure, but the operating principle in the motor is that you will put oil in a motor and the shaft is spinning, and in a pump, of course, so that you will spin the shaft and you will pump the oil. But sometimes even the very same component can work either as a pump or as a motor. These motors are divided based on the rotating speed. You can call, or you can have a slow speed range, middle speed range, or high speed range motors. Tomorrow I'm going to talk more about hydraulic pumps, and at the same time you will see what kind of different construction types there are for the motors as well. Also tomorrow I'm going to talk more about these formulas, how to calculate and dimension these motors, or not motors, but the pumps. But the formulas are the same for motors, but these efficiencies are other side of the line, to say so, because of course the efficiency works in a different way, whether you are creating torque or whether there is a demand for torque.
Simo, but what are applications for hydraulic motors? I mean, it's probably very hard to control speeds and to adjust speed with the hydraulic motors. So
not so hard. They are very common in mobile machinery propulsion. So there can be so-called hydrostatic transmissions. For example, an agricultural tractor, when you drive with that one in a forest, or an excavator, there are hydraulic motors to spin the wheels.
Wow, but is it used instead of combustion engine, or?
Of course, there is first a combustion engine, but normally there is not an. The combustion engine is spinning the hydraulic pump, and then you have this hydraulic energy, and then the hydraulic energy is very easy to control, and then you will use the hydraulic motors to drive forward or reverse with these vehicles, and it works very well in a such system where the driving speeds are slow, but you need a very high force. It's not so it's not so suitable for driving on road, but it is very functional in off-road systems.
Okay, so is it, well, a couple of years ago, I had experience with forklifts, and sometimes like the hydraulic cylinders didn't work and they didn't lift the fork, and it was needed to rev the combustion engine first. Why was it? Like to increase pressure in system, or?
Okay, this is interesting. So please repeat, what did you have to do so that you made them work again?
Just rev the combustion engine.
Press more gas.
Gas pedal, exactly.
Then I think simple. There was not enough power from combustion engine to spin the pump, and maybe the pump was already a little bit old one, so that there was some leakages in the pump, and you needed to rotate it higher speed so that you can overcome all the leakages, and then it would only after then it would be able to generate the needed pressure and needed flow for the cylinders.
So it's not a standard practice to do this. I mean,
no,
just malfunction system.
Yes, I would say so. But it is of course if you want to make the cylinder move faster, then you need to press more gas so that the spinning speed of the pump becomes higher, and the flow rate that it generated is also higher. So it might be that in the idle it moves very, very slowly, and this is normal. But if you want them to move faster, then you need to hit the gas pedal.
So these systems, like, they are not isolated, they connected between each other. So the hydraulic system is somehow interacts with combustion engine.
Of course, yes, because the combustion engine gives the power to hydraulic system.
Well, it makes sense. Yeah, thank you.
Actually, you see it in this formula. This Q stands for the flow rate, and the N stands for the rotating speed, and this VK is so-called volume of the pump or of the motor, that how much volume it can transmit when it spins one round. And you can see from this formula that if you are idling with your internal combustion engine, you get small amount of flow rate, but if you then hit the gas pedal and your rotating speeds comes higher and higher, you get more and more flow rate.
Yeah, and what is ETA, like the Greek letter? Is it for efficiency?
Yes, this is efficiency, yes.
Okay.
But tomorrow I will talk more about this, and I think that then you will understand this even better, how it operates. And one special motor type that I just want to introduce here today is this radial piston motor. And actually this operates in such places that I already mentioned, this not agricultural, but forest tractors, for example, so that the same component works as a wheel hub and a wheel motor. You don't need to have any other mechanical support or anything. You can just attach a wheel and a rim here directly to this motor and then spin it. It is very common in these mobile applications, in these hydrostatic transmissions that I just mentioned. And this kind of a hydrostatic transmission, if we jump a little bit back to the very first lecture, not here, but maybe it was in here. Introduction, if you still remember. So this hydrostatic transmission can work, for example, here to make movement of this excavator or this kind of forest tractor possible. And in many cases, it's this kind of a closed loop circuit, so that you have an hydraulic pump here, and now the internal combustion engine would be here, and the internal combustion engine would be rotating the hydraulic pump, which will generate the flow, which will go to the hydraulic motor, which is connected directly to the wheel. And then the flow comes from a motor back to hydraulic pump. Does it make sense?
Yes.
And how to control then the driving speed? It is the pump. That this arrow means that you can change something, and in this case you can change the so-called pump angle. And when you do that, you are controlling that how much flow rate you are generating. And when you generate the flow or control the flow rate, you are controlling that what is the rotating speed of the motor, and in the same way you control what is the driving speed of the vehicle. And it is very simple and very straightforward, and it works very well in excavators or forest tractors when you have this slow driving speeds, but you need this very high torque. But like I mentioned, when you go to drive on the road, the efficiency becomes very pure, and then it makes sense to have the normal mechanical gearbox or something like that instead of this. Okay, but that was everything that I wanted to say about the actuators and cylinders and motors today. And now I can open the breakout rooms, and if you want to discuss about your projects, I have some time for that. And then tomorrow we will continue this hydraulics lecture, and then I'm going to talk more about these hydraulic pumps. And also we have some time to discuss about the projects tomorrow.
Thank you.
Thank you. And I will open the breakout rooms, and you are able to join to the breakout room by yourself, and then press this ask for help button if you want that I will come there to speak with you. Is it clear?
Absolutely.